Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Engineering and Technology, SOET, Certificate Programs, Postgraduate Certificate, Certificate in Condition Monitoring, CCOMO, MET-001 Metrology, Instrumentation and Tribology, Block-1 Principles of Measurement and Measuring Techniques, Unit-1 Standard of Measurement. 1.1 Introduction. In order that the investigators in different parts of the country and different parts of world may compare the results of their experiments on a consistent basis, it is necessary to establish certain standard units of length, weight, time, temperature and electrical quantities. The National Bureau of Standards has the primary responsibility for maintaining these standards in the United States. In India, Indian Standard Institute, ISI, New Delhi has taken the responsibility for maintaining all the standard measurements. 2. Monitor the standard of measurements. The same institute issues instructions to put ISI mark on measuring instruments and items so that these may be compared with non-standard ones. In the measurement system, the quantity to be measured, in the direct method, is compared directly against a standard of same kind of quantity. The magnitude of quantity being measured is expressed in terms of a chosen unit for the standard and a numerical multiplier. A length can be measured in terms of meter and a numerical constant. Thus, a 10-meter length means a length 10 times greater than a meter. Thus, by the means of standard, it is possible to provide means of establishing and maintaining the magnitudes of the various units. The simplest kind of standard is a physical object having desired property. This standard can be used as a basis of comparison. Objectives. After studying this unit, you should be able to understand the importance of standard in the measurement systems, explain the sources and causes of errors in the measurements, and perform the analysis of experimental data to find the accuracy, precision and the general validity of the experimental results. 1.2 Standards of measurements and their classification. The standards of measurements are very useful for calibration of measuring instruments. They help in minimizing the error in the measurement systems. On the basis of the accuracy of measurement, the standards can be classified as primary standards and secondary standards.
1.2.1 Primary standard. A primary standard quantity will have only one value and it is fixed. An instrument, which is used to measure the value of primary standard quantity, is called primary standard instrument. It gives the accurate value of the quantity being measured. No precalibration is required for this instrument. It is used to calibrate the instruments having less accuracy. By comparing the readings of the two instruments, the accuracy of the second instrument can be determined. 1.2.2 Secondary standard. The value of the secondary standard quantity is less accurate than primary standard one. It is obtained by comparing with primary standard. For measurement of a quantity using secondary standard instrument, pre-calibration is required. Without calibration, the result given by this instrument is meaningless. Calibration of a secondary standard is made by comparing the results with a primary standard instrument or with an instrument having high accuracy or with a known input source. In practical fields, secondary standard instruments and devices are widely used. Using calibration charts, the error in the measurement of these devices can be reduced. 1.3 Standard unit of length. The meter is considered as one of the fundamental unit upon which, through appropriate conversion factors, the English system of length is based. The SI unit of length in meter. The standard meter is defined as the length of a platinum iridium bar maintained at very accurate conditions at the International Bureau of Weights and Measures at Sèvres, near Paris, France. All other meters had to be calibrated against the meter. The conversion factor for length for English and metric systems in the United States is fixed by law as 1 meter equals 39.37 inches. Secondary standard of length is maintained at the National Bureau of Standards for calibration purposes. In 1960, the General Conference on Weights and Measures defined the standard meter in terms of the wavelength of the orange-red light of a Krypton 86 lamp. The standard meter is thus 1 meter equals 1,650,763.73 wavelengths of orange-red light of Krypton 86. In 1982, the definition of the meter was changed to the distance light travels in 1/299,792,458 of a second. For the measurement, light from a helium neon laser illuminates iodine which fluorescences at a highly stable frequency. The inch is exactly defined as 1 inch equals 2.54 centimeters equals 0.0254 meters. In FPS system, the fundamental unit is foot. Its conversion factor can be derived from its smaller unit and is given by 1 foot equals 12 inches equals 12 times 2.54 centimeters equals 30.48 centimeters equals 0.3048 meters. The other derived units and their conversion factors are as follows. 1 yard equals 3 feet equals 0.9144 meters. 1 mile equals 1760 yards equals 1609.344 meters. In CGS system, the fundamental unit of length is centimeter. Its conversion factors for other system are already mentioned above. The derived units for length are as follows. 1 meter equals 100 centimeters. 1 kilometer equals 105. cm equals 1000 meters. 1 millimeter equals 10-3 meters equals 10-1 centimeter. 1 centimeter equals 10-2 meters. 1 decimeter equals 10-1 meter. 1 decameter equals 10 meters. 1 hectometer equals 102 meters. We also have some other units, which are frequently used for short and large lengths. They are 1 Fermi equals 1 F equals 10 to 15 meters. 1 angstrom equals 1 A equals 10 power minus 10 meters. 1 light year equals 9.46 into 10 power 15 meters, the distance that light travels in 1 year. Note, velocity of light is 8.310 meter per second. 1.4 Standard unit of weight. The kilogram is considered as fundamental unit upon which, through appropriate conversion factors, the English system of mass is based. The SI unit of mass is kilogram. The standard kilogram is defined in terms of platinum iridium mass maintained at very accurate conditions at the International Bureau of Weights and Measures in Sèvres, France. The conversion factors for the English and metric systems in the United States are fixed by law is 1 pound mass equals 453.59237 grams equals 0.453592237 kilogram. Secondary standard of mass is maintained at the National Bureau of Standards for calibration purpose. In MKS and SI systems, fundamental unit of mass is kilogram, whereas in CGS system, the unit for the same is gram. The conversion factors for the above units and units derived from them are as follows. 1 kilogram equals 1000 grams, 1 gram equals 10 to 3 kilogram. 1 hectogram equals 100 grams equals 10 to 1 kilogram. 1 decagram equals 10 grams equals 10 to 2 kilogram. 1 milligram equals 0.001 gram equals 10 to 6 kilogram. 1.5 Standard unit of time. The standard units of time are established in terms of known frequencies of oscillation of certain devices. One of the simplest devices is a pendulum. A torsional vibration system may also be used as a standard of frequency. The torsional system is widely used in clocks and watches. Ordinary 50 Hz line voltage may be used as a frequency standard under certain circumstances. An electric clock uses this frequency as a standard because it operates from a synchronous electric motor whose speed depends on line frequency. A turning fork is a suitable frequency source, as are piezoelectric crystals. Electronic oscillator may also be designed to serve as very precise frequency sources. The SI unit of time is second. The fundamental unit of time, the second, has been defined in the past as 1/86400 of a mean solar day. The solar day is measured as the time interval between successive transits of the sun across a meridian of the Earth. The time interval varies with location of the Earth and time of the year, however, the mean solar day for 1 year is constant. The solar year is the time required for the Earth to make one revolution around the sun. The mean solar year is 365 days 5 hours 48 minutes 48 s. The above definition of second is quite exact but is dependent on astronomical observation in order to establish the standard. In October 1967, the 13th General Conference on Weights and Measures adopted a definition of the second as the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the fundamental state of the atom of cesium-133. This standard can be readily duplicated in standards laboratories throughout the world. The estimated accuracy of this standard is 2 parts in 109. Very precise frequency and time standards are broadcast by National Bureau of Standards radio station, WWV. This station furnishes standard time intervals, time signals, standard musical pitch, standard radio frequencies, and radio propagation forecasts. The accuracy of the radio and audio frequencies, as transmitted, is better than 1 part in 100 million, and the time interval is accurate to 1 part in 100 million plus 1 microsecond, µs. 1.6 standard unit of temperature. An absolute temperature scale was proposed by Lord Kelvin in 1854 and forms the basis for thermodynamic calculations. This absolute scale is so defined that particular meaning is given to the second law of thermodynamics when this temperature scale is used. Table 1.3, Interpolation Procedures for International Practical Temperature Scale of 1968. Look at the screen. Table 1.4, Fixed Points for International Temperature Scale of 1990. Look at the screen. Both the Fahrenheit, O, F, and Celsius, O, C, temperature scales are in wide use, and they experimenters must be able to work in either. The absolute Fahrenheit scale is called the Rankine, O, R, scale, while absolute Celsius has been designated as the Kelvin, K, scale. K equals degree C plus 273.15. Degree R equals degree F plus 459.67. The SI unit of temperature is Kelvin. 1 Kelvin is equal to the fraction 1/273.6 of the thermodynamic temperature of triple point of water. 1.7 standard units of mechanical quantities. Among the various mechanical quantities, velocity, acceleration, force, work, energy and power are some of the important quantities of them. All these quantities may be expressed in terms of the fundamental dimensions, length, L, mass, m, time, t, and temperature, theta. The unit to be used for certain dimensions are selected by somewhat arbitrary definitions which usually relate to a physical phenomenon or law. For example, Newton's second law of motion may be written as force equals time rate of change of momentum. F equals k into d upon dt, mv, 0.1.1. Where k is the proportionality constant. If the mass is constant, F equals kma, 0.1.2. Where the acceleration is equals dv upon dt. EQ, 1.2, may also be written as F equals ma upon gc, with 1 upon gc equals k. 1.3. EQ, 1.3, is used to define our systems of units for mass, force, length and time. Some typical systems of units are: a 1 pound force will accelerate 1 pound mass 32.174 feet per second square. B. 1 pound force will accelerate 1 slug mass 1 foot per second squared. C. 1 dyne force will accelerate 1 gm mass 1 centimeter per second squared. D. 1 Newton, N, force will accelerate 1 kilogram mass 1 meter per second squared. A. 1 kilogram force will accelerate 1 kilogram mass 9.80665 meter per second squared. The kilogram force sometimes given the designation kilopond, kp. Since EQ, 1.3, must be dimensionally homogeneous, we shall have a different value the constant gc for each of the unit the system in items, a, to, a, above. The values are:
A. gc equals 32.174 lbm. ft, lbf. S square. B. gc equals 1 slug. ft, lbf. S square. C. gc equals 1 gram. cm, deen, s. D. gc equals 1 kilogram, m, n, s square. A. gc equals 9.80665 kgm meter per kilogram force. S square. It does not matter which system of units is used so long as it is consistent with the above. Definition. Work has the dimensions of a product of force times a distance. Energy has the same dimensions. Thus, the units for work and energy may be chosen from any of the system used above as: A. lbf, featuring B. lbf, featuring C. 1 deen, cm equals 1 erg. D. 1 n, m equals 1 joule, j. A. 1 kilogram force, m equals 9.80665 j. In addition, we may use the units of energy which are based on thermal phenomena. A 1 British thermal unit, BTU, will raise 1 pound mass of water 1 degree Fahrenheit at 68 degrees Fahrenheit. B. 1 calorie, cal, will raise 1 gm of water 1 degree Celsius at 20 degrees Celsius. C. 1 kilocalorie will raise 1 kilogram of water 1 degree Celsius at 20 degrees Celsius. The conversion factor for the various units of work and energy are 1 BTU equals 788.16 lbf. FT. 1 BTU equals 1055 J. 1 kilocalorie equals 4182 J. 1 BF, featuring equals 1.356 J. 1 BTU equals 252 calories. The weight of a body is defined as the force exerted on the body as a result of the acceleration of gravity. Thus, W equals G upon Gc into m, where W is the weight and G is the acceleration due to gravity. Note that the weight of a body has the dimensions of a force. We now see why systems, to A, above were devised. 1 lbm will weigh 1 bf at sea level, and 1 kgm will weigh 1 kilogram force. Unfortunately, all the above unit systems are used in various places throughout the world. While the foot-pound force, pound mass second, degree Fahrenheit, BTU system is still widely used in the United States, there is increasing impetus to institute the SI units as a worldwide standard. The system which is now internationally accepted is the System A. International Unites, abbreviated as SI. Here we have 7 basic units. They are the meter, m, for length, the kilogram, for mass, the second, s, for time. Kelvin, K, for temperature, ampere, A, for electric current, candela, CD, for light. Intensity and mole, mo, for amount of substance. In this course, we shall follow SI units. Derived units. The units of all other physical quantities can be expressed in terms of these base units. For example, we can express the unit of speed in meter per second, the unit of density in kilogram per cubic meter. Let us consider another physical quantity like force. From Newton's second law of motion, force can be defined as the product of mass and acceleration. We can therefore take the unit of force as 1 kilogram times 1 meter per second 2. We call this by the name, Newton for convenience. The unit of energy is Newton meter. We call this by the name Joule. The unit of power is Joule per second. We call it Watt. The conversion factor for various units are 1 HP equals 746 Watt, J, S. 1 HP equals 550 feet minus 1 B, sec. 1 HP equals 75 kilograms M, sec. 1.8 standard unit of luminous intensity of a source of light. Candela is the SI unit of luminous intensity of a source of light in a specified direction. The candela is the luminous intensity of a black body of surface area 1/60,000th of a meter square. Placed at the temperature of freezing platinum and at a pressure of 101,325 N/m square in the direction perpendicular to its surface. Now candela is redefined as the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 times 1012 Hz and that has a radiant intensity in that direction of 1/683 watt per steradian. SI unit of solid angle. 1.9 standard unit of amount of substance. The mole, mo, is the SI unit of amount of substance. 1 mole is the amount of substance of a system that contains as many elementary entities as there are atoms in 0.012 kilograms of carbon-12. 1.10 standard units of electrical quantities. The International Conference on Electrical Units in London in 1908 confirmed the absolute system units adopted by the British Association Committee on Electrical Measurement in 1863. This conference decided to specify some material standard which can be produced in isolated laboratories and used as international standards. The desired properties of international standards are that they should have a definite value, be permanent, and be readily set up anywhere in the world, also that their magnitude should be within the range at which the most accurate measurements can be done. The 4 units, ohm, ampere, volt and watt, established by above specifications were known as international units. The ohm and ampere are primary standards. Definitions of international unit are given below. International ohm. The international ohm is the resistance offered to the passage of an unvarying electric current at the temperature of melting ice by a column of mercury of uniform cross-section, 106.300 cm long and having mass of 14.4521 gm, i.e., about 1 sq.mm in cross-section. International ampere. The international ampere is the unvarying current which when passed through a solution of silver nitrate in water deposits at the rate of 0.00011118 gm per second. The international volt and watt. The international volt and watt defined in terms of international ohm and ampere as constructing standards, which did not vary appreciably with time, was difficult, and also as, by 1930, it was clear that the absolute ohm and ampere could be determined as accurately as the international units. The International Committee on Weights and Measures decided in October 1946 to abandon the international units and choose January 1, 1948 as the date for putting new units into effect. The change was made at appropriate time, and the absolute system of electrical units is now in use as the system on which electrical measurements are based. Following a number of determinations, by various national laboratories of standards, of the absolute ohm and ampere during the year 1934 to 1940, the National Physical Laboratory has adopted the following conversion factors. 1 international ohm equals 1.00049 absolute ohm. 1 international ampere equals 0.99985 absolute ampere. 1 international volt equals 1.00034 absolute volt. 1 international watt equals 1.00019 absolute watt. 1 international Henry equals 1.00049 absolute Henry. 1 international Farad equals 0.99951 absolute Farad. Electrical standard. Voltage standards. To make voltage measurement, it is desirable that we should have a cell whose EMF remains constant and is accurately known. It must be made of chemicals which can be purified and reproduced easily. No chemical reactions must take place inside the cell except when the current is drawn from it. Such a cell is called standard cell. Standards of capacitance. As the capacitance of primary standards are calculated from its dimensions, it is essential that the shapes of the capacitors must be in simple geometrical form so that the dimensions can be measured easily. For this reason, three types of primary standards, namely the concentric spheres type, coaxial cylinder type with guard rings, and parallel plates type with guard plates are used. All capacitors used in AC bridges are secondary standards. These are calibrated standards. 1.11 Summary. On the basis of the accuracy of measurement, the standard can be classified into two categories, viz. Primary standard and secondary standard. The meter is considered as one of the fundamental units upon which, through appropriate conversion factors, the other systems of length are based. The kilogram is considered as fundamental unit upon which, through appropriate conversion factors, other systems of mass are based. The standard units of time are established in terms of known frequencies of oscillation of certain devices. The fundamental unit of time is second. Both Fahrenheit, O, F, and Celsius, O, C, scales are widely used for measurement of temperature. The absolute Fahrenheit scale is called Rankine, O, R, scale, and absolute Celsius has been designated as the Kelvin, K, scale. The relationship between these scales is as follows. K equals degree C plus 273.15. Degree R equals degree F plus 459.67. In mechanical systems, the fundamental units in SI system are meter, Newton, kilograms, second, and joule. International units of electrical systems are ohm, ampere, volt, and watt. The SI unit of luminous intensity of light is candela, CD, and the SI unit of amount of substance is mole, mho. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.